So where we're headed now is we're going to now talk about ion solubility in water. Again, this is one of those issues that's really, really important for the basis of all life. And that is ions, because they're charged, easily go into solution in water because of the dipole moment in water. So what I want to think about here is to take a beaker of water, which is 1 liter, and at the bottom of this beaker of water, is a crystal of sodium chloride. Now, we're going to put some numbers to this. We're going to say this is 5.84 grams in 1 liter. Now, as a crystal, the sodium chloride crystal has an ion of sodium interacting directly with a chloride ion. Sodium is positively charged, chloride is negatively charged. And in a crystal, the salt that you shake out of your salt shaker is crystalline sodium chloride. And in that crystal, each sodium ion is associated with a chloride ion over and over again, millions upon millions upon millions of them. But we can take the sodium chloride crystal and put it into water. And we've all done this. Sitting around the dinner table, we can take the salt shaker and shake some salt into the water. And you know what's going to happen. That sodium chloride is going to go into solution in the water. We're going to take that idea and simply turn it around a little bit and say we're going to put the sodium chloride down here at the bottom. Then we're going to raise the volume of water up to 1 liter. And then we're going to imagine what's happening to the sodium ions and the chloride ions, which are initially locked in a crystal structure of sodium chloride. We're going to say we have 5.84 grams in 1 liter because it turns out there are 58.4 grams per mole of sodium chloride. So every mole of sodium chloride weighs 58.4 grams. Well, we're going to simplify that, move the decimal place 1, so we have 5.84 grams. We're going to put it in a liter of water so that we get 5.84 grams per liter. And this comes out to 0.1 molar, which is the same as 100 millimolar. Okay, well, how does that happen? Well, remember that as we were discussing before break, there are these water molecules in here. And the water molecules, again, have these partial charges. And certainly they're interacting one with another through those hydrogen bonds. But they're bouncing around because of thermal energy. There's a certain amount of heat and energy in here where these molecules are bouncing around. And now and again, they'll bounce into this crystal of sodium chloride. There's enough energy in these water molecules as they're bouncing around that they can cause the liberation of a sodium and a chloride into the water. And you know this intuitively. You know that if you want something to go into solution in water, you heat it up. You give it more energy. You get the water molecules bouncing around with more energy, so they'll effectively more efficiently chip off the sodium and the chloride ions. The sodium ion comes off. We'll show it as orange. Now, it's no surprise that the positive charge on the sodium is going to interact with the negative oxygen on the water. Remember, these water molecules are free to spin and rotate around, but as they spin and rotate around, the negative end of the oxygen is most likely to spend a little more time with the sodium. Similarly, when the chloride comes off, and I'll show you this is green, it too will be surrounded by a cloud of water. But in this case, because the positive charge on the positive charge on hydrogen is most likely to interact with the negative charge on chloride, now what we see is the chloride is surrounded by a cloud of water. They're surrounded by something known as a shell of hydration. So that around each of these sodium ions and around each of the chloride ions, we'll see that there is a cloud of water that is around each of the ions. The water molecules are still interacting one with another through their hydrogen bonds, but the charges on the water are also allowing them to interact with the charges on the chloride and the sodium. It's the charge characteristics of the sodium and the chloride which allow these charged particles to easily go into solution in water. Yes? The question is, does this affect surface tension like dish soap does? Probably not in the same way, because these will have a cloud of water around them, but they'll also be interacting with waters out here. What happens with the detergent is that, we'll talk about this a little bit when we talk about phospholipids, but the detergents will have a charged end and an uncharged end. So the charged end of a detergent will interact with the water molecule, but it'll have this tail. And the tail then provides a kind of insulating layer so the other water molecules can't effectively interact with, it'll form a tail so that water molecules can't interact with one another sufficiently because of that hydrophobic tail. It's like a barrier, exactly. It's kind of like insulation. So they can, but here you don't have that because you have such a strong charge on the chloride and such a strong charge on the sodium. And you get this, and two things come from this. First, that it's because of the charge on the sodium chloride that the sodium and chloride can go into solution. What's more is the sodium and chloride ions go so completely into solution that they don't spend much time anymore interacting with one another as sodium ions and chloride ions. They're almost exclusively interacting with the dipole moments on the water. They go completely into solution. It's this charge characteristic which allows the ions to go into solution. And the other thing I should point out here is that because the sodium and the chloride completely dissociate into a sodium ion and a chloride ion, that this 0.1 moles of sodium chloride, remember this is 0.1 moles of sodium chloride, that the 0.1 moles of sodium chloride dissociates into 0.1 moles of sodium ions and 0.1 moles of chloride ions. This is going to have important implications later on when we talk about osmolality and the movement of water. But for now, just recognize that these ions are now leaving their interaction one with another in crystal and going into solution. The other idea I want to try to get to in this simple description is the idea of diffusion. It's difficult for me to overemphasize how important this concept is and what we're going to be talking about for the next 8 weeks. Diffusion is simply the idea of molecules or ions move randomly. And because of this random motion, the random movement, because we can't predict which direction they'll take, and they move off in any old direction, it's completely chosen at random, it's stochastic, we find that on average, molecules move from regions of high concentration to regions of lower concentration. So again, you can imagine that if we start down here with a solid crystal of sodium chloride, and now the water molecules are bouncing against this crystal and chipping off one ion at a time, that initially the concentration of sodium ions in water will be pretty high right around the sodium chloride crystal. But given time, as these randomly wander about, as they bounce one against another, as they randomly move, they now become randomly distributed in the water column. Such that after a period of time, if you look down here in this corner, the probability of finding a sodium ion or chloride ion is the same as if you look up here in this corner. We now have a random distribution throughout the column of water. We have reached a kind of equilibrium where these ions are randomly distributed. We can think about this intuitively. If, for example, I put an open bottle of perfume in the middle of the room, effectively those perfume molecules are going to diffuse just like the sodium chloride. Those perfume molecules are volatile. They'll leave their fluid in the bottle and go out into the air. As they go out into the air, they now begin to bounce against the oxygen and nitrogens and become buffeted about. So initially, the people who will smell that perfume will be right around the middle of the room where the perfume is originating. But over time, as these molecules leave the pool of perfume and they go out into the room and they get buffeted and randomly distributed, everyone in each corner of the room, wherever they are, will be able to smell that perfume because it's become randomly distributed. And if we close the bottle of perfume so that we no longer have a source of the perfume, those molecules will be randomly distributed through the room after a few minutes, simply because of the action of the air molecules on the perfume, or in this case, the action of the water molecules on the sodium and chloride, buffeting them about, moving them to a random distribution in the water column. This is the idea of things going from higher to lower concentration. We started out with a high concentration and no concentration up here, but given enough time, these sodium and chloride ions will be evenly distributed throughout the